Okay, here we go for the Honors Unit 7 test review on electron configuration and the periodic table. Which of the following has the longest wavelength? Well, the longest wavelength corresponds to the lowest frequency, which would mean the lowest energy. So if we look at infrared, ultraviolet, and visible light, okay, ultraviolet is above the visible light spectrum and infrared is below the visible light spectrum. So ranking them in order of lowest to highest energy, this is the lowest, this is the medium, this is the highest of those three. So the one with the longest wavelength is the one with the lowest energy, which would be infrared. Which set of quantum numbers is possible for the highest energy orbital found in the ground state of the antimony atom? Well, first we need to look up on the periodic table and find out where antimony is and what the end portion of its electron configuration is going to be. And we find that antimony is in the 5th row, so it's going to have a principal quantum number of 5. That eliminates a couple of choices right away. It is in the p block on the right-hand side, and it's in the 3rd column of the p block. So we've got the principal quantum number 5. That's the first one. So it's going to be one of these 3 remaining choices. The second quantum number corresponds to the sublevel. And so S is 0, P is 1, D is 2, F is 3. So it has to be 1 for the second quantum number, so that eliminates the middle choice. So now we're down to the last 2. The third quantum number corresponds to an orbital within a sublevel. So within the p sublevel, well, in all sublevels, the middle orbital is 0. And then it goes positive and negative in either direction. So for the s orbital, all you have is the 0. For the p orbital, you have a -1 on the left, a +1 on the right. And then if we had the d orbital, there'd be a -2 and a +2, and so on. So we've actually kind of already figured this one out. But just to show you the final step, so it's +1, which would be this orbital over here, and as far as the spin at the end, the last quantum number, the first electron in any orbital always has a +1/2 spin. If there were 2 electrons in this orbital, the second one would have a -1/2 spin. So the 4 numbers are the principal energy level, which is the row, the sublevel, 0, 1, 2, or 3, the orbital within the sublevel, starting with 0 in the middle and going negative to the left, positive to the right, and then the 4th quantum number is the spin. The first electron in an orbital has a positive spin, the second electron in an orbital has a negative spin. Bohr's theory of the hydrogen atom assumed that the electron can exist in any of a set of discrete states and can move from one to another by emitting or absorbing radiation. This was kind of the key concept in Bohr's model. This gives rise to the nucleus with the distinct ring pattern around it, electrons jumping from one orbital to another, and when they move back down, they give off light. This was his explanation for the phenomena of atomic emission spectra and the idea that electrons could only jump in specific ways was the beginning of quantum mechanics and the modern quantum model of the atom, because he said that electrons could be in one place or another and never in between. Which of the following combinations includes all the true statements from this list and none of the non-true statements? So let's look at the statements. Electrons fall to a lower energy level. It emits electromagnetic radiation. That's true. So it's got to be Z1. The energy of electromagnetic radiation is directly proportional to its frequency, which means when the frequency increases, the energy increases. This is also true. So I have to have Z1 and Z2. So is the third one true? The product of the wavelength and the speed of light is the frequency. That is false. Okay, the speed of light divided by the wavelength equals the frequency, not the wavelength times the speed of light. So the correct combination is Z1 and Z2 only are the two true statements, and the third one is false. An electron in a hydrogen atom could undergo any of these, which would give the shortest wavelength. Okay, the shortest wavelength is the light with the highest energy. So in order to get the highest energy, when you have a choice where the final position is N1, that's always going to be the highest choice. So we can eliminate anything that does not end on the first energy level. And then the question is, well, which of the remaining choices is going to have the highest or give off the most energy? Well, when you narrow it down to they all end in the same place, the one that's going to have the highest energy is the one that transitions the farthest. So going from the greatest difference in energies. The fourth energy level has a lower overall energy in terms of giving off and absorbing energy than the third or the second, because it's farther from the nucleus, so it takes less energy to get out there once you're out there. So when looking at the transitions, look for a final position N1, and then from there find the biggest difference, or all other things being equal, if they were all, say, N2 for the final position, you would look for the biggest difference to find the greatest energy. How many electrons can possess quantum numbers with a principal quantum number of 4 and a magnetic quantum number of -1? Well, on the fourth energy level, so N4 has all 4 of the sublevels that we talk about, S, P, D, and F. So how many of those energy levels and sublevels possess a -1 orbital? Well, S only has a 0 orbital. P has a 0, a -1, and a +1. D has 0, -1, -2, +1, +2. And then F, 1, 2, 3, 4, 5, 6, has 0, -1, -2, -3, and +1, +2, +3. Okay, so we're really concerned with, now we have how many, because these would have different angular momentum numbers. Right, this would be 0, this would be 1, this would be 2, this would be 3, but they're not asking us about that. So any orbital with a magnetic quantum number of -1 would fall into this category. So how many of those do we have? Well, we have 3 with a -1 number. Each of those orbitals could hold 2 electrons, so 3 times 2 means there could be 6 different electrons with those 2 quantum numbers. Okay, they would have different angular momentum numbers, and they would have different spin numbers, but they would have the same principal number and the same magnetic quantum number. Okay, which of the following measures the tendency of an atom to attract electrons to itself? Okay, so we have different measurements of how atoms interact with electrons. Ionization energy is how strongly an atom holds onto its own electrons. The higher the energy, the harder it is to get electrons away. The measure of how strongly an atom pulls on other atoms' electrons in a bond is electronegativity. And then these last 2 choices are just not anything we've talked about yet. Which of the following has the smallest atomic radius? So the trend overall in atomic radius is that it decreases from left to right, and it increases from top to bottom. So increase, decrease. So if we're looking for the smallest atomic radius, and if we assume, or if we look on the periodic table, all these elements are in the same row, so we don't need to worry about going from one period to another. So if we line them up in the order they appear, we have silicon, let's see, aluminum is the first one, then silicon, then phosphorus, then sulfur, then chlorine. Okay, 1, 2, 3, 4, 5. So the one that's going to be the smallest is the one that appears farthest to the right on the periodic table. And in this case, out of these 5 elements from left to right, chlorine is the one farthest to the right. So that's going to be the smallest atomic radius. What is the primary reason for the trend in atomic radius going from left to right as we move across the periodic table? Well, the reason kind of overall for all of the trends, whether it's atomic radius, ionic radius, ionization energy, electronegativity, they all are more or less related to the same thing, which is that as you go from left to right, and this is just talking about going across, going up and down is a different thing, but as you go from left to right, you're adding electrons to the same energy level, so essentially the same distance from the nucleus, while adding protons to the nucleus. So the positive charge is getting more concentrated, so that's what the effective nuclear charge refers to. So it's getting stronger in the center, while the electrons on the outer ring are not getting any farther away. So the nuclear charge in the middle gets stronger, the electrons on the outside aren't getting any farther away, so in the tug of war, the protons in the nucleus start to draw those electrons in a little bit closer, which makes the radius smaller. Okay, so now we've got ions, and we want to arrange them in increasing atomic radius. So we want the largest radius at the end. So the first thing to look at is the fact that beryllium with a charge of +2 is going to be the smallest, okay, because the more electrons that are given up, the more the remaining electrons get pulled in. So that kind of right away tells us it's going to be this choice. But just to sort of play it out and keep in mind which is which, the rest of the trend has to do with the fact that lithium, sodium, and potassium are all in the same group, and they go in this order. As you go down, they're all +1 charges. So the way to distinguish is, well, they've all lost 1 electron, but where did those electrons come from? Well, in lithium, it came from the 2nd energy level. In sodium, it came from the 3rd, potassium from the 4th. So the electrons in potassium were taken from much farther from the nucleus than the electrons in either sodium or lithium. So even though they've all lost electrons and gotten smaller than they were when they were neutral, the comparison is the smallest ones are on the top and the biggest ones are on the bottom. So again, that gives us this order. Beryllium with a +2 charge is the smallest, and then from there you go top to bottom within a group: lithium, sodium, potassium. What is the energy of a microwave photon with a frequency of 2.5 times 10 to the ninth hertz? Well, energy is found by multiplying Planck's constant times the frequency. Planck's constant is 6.626 times 10 to the -34th. And then we're going to plug those numbers in, and we get 6.626 times 10 to the -34th times the frequency of 2.5 times 10 to the 9th hertz. When we multiply those two numbers together, we end up with 1.66 times 10 to the -19th, and the unit here for energy is joules. That's energy equals. What is the energy of a photon emitted when an electron from hydrogen atom falls from the 4th to the 2nd energy level? We need the Rydberg equation. You'll be given the Rydberg equation on a reference sheet as part of the test, along with the speed of light and Planck's constant, which was in the last problem. You'll also be given a little bit more information that will be used for one of the problems that we'll get to. So what is the energy of a photon emitted? So the Rydberg equation says that the change in energy is -2.18 times 10 to the negative 18th joules times 1 over the square of the final energy level, which is 2 squared, minus the inverse square of the initial energy level. And when we do that out, we've got energy negative 2.18 times 10 to the negative 18th joules times 1/4 minus 1/16, and we do that out, and we end up with 4.09 times 10 to the negative 19th joules. Now, if you were asked what color light that might be, you would take the energy, convert it to frequency, because energy equals frequency times Planck's constant. So you could do the energy divided by Planck's constant to get the frequency. So just, if I was going to do that out, it would look like this. Okay, and then you would divide the speed of light by the frequency to get the wavelength. Okay, once you have the wavelength, you can find the color on the chart. That's the other piece of information I was referring to. You'll be given a set of wavelengths for different colors of visible light, because you will be asked to do a problem similar to this one, but you'll be asked to identify the color that the light would be. So you find the energy using the Rydberg equation, and then divide that by Planck's constant, which equals the frequency, and then the speed of light divided by the frequency gives you the wavelength. Look up the wavelength on the color chart and identify the color. Okay, given a group of elements and a list of their ionization energies, basically we're ranking these elements in terms of their ionization energy, is what the question is asking us to do, from largest to smallest, or actually just match them up. Well, ionization energy increases as you go from left to right, and it decreases as you go down from one to another, from one row to another. So the one that is highest and farthest to the left is chlorine. So chlorine is going to have the highest of the energies here, which is 1255. And then next we go down a row, and then we have to compare potassium and germanium, which are in the same row. So they're both going to be lower than chlorine. We just have to decide which is in the middle and which is at the bottom of the list. Well, ionization energy increases from left to right. So the one to the right is going to have the higher ionization energy. The one that's higher, or sorry, more to the right, is germanium, because potassium is at the far left, germanium is in the P block on the right-hand side. So germanium is going to be the second highest energy of this group, and that means that potassium is the lowest energy in terms of ionization energy. So when we do that, we end up with this combination here. Chlorine is the highest because it's higher up and farther to the right. Germanium is higher than potassium because it's farther to the right. And then potassium is the lowest because it's on the left. Okay, we have to calculate the wavelength of light emitted during a transition. So this is very similar to the example I was giving you a couple of minutes ago. So first we're going to do the Rydberg equation. And we have change in energy equal to negative 2.18 times 10 to the negative 18th joules times, we're going to a final of 2 squared minus 5 squared. So change in energy, negative 2.18 times 10 to the negative 18th times 1/4 minus 1/25. and that gives us negative 2.18 times 10 to the negative 18th times 0.21, which gives us for energy 4.578 times 10 to the negative 19th joules. Now to convert that to frequency, I'm going to divide by 6.626 times 10 to the negative 34th. That gives us a frequency of 6.909 hertz. And then if we take 3.00 times 10 to the 8th divided by 6.909 times 10 to the 15th. Keep that scientific notation there. So the speed of light divided by the frequency equals the wavelength, which comes out to 434.2 nanometers, which would be 4.347 times 10 to the negative 7th meters, just in case that's what you ended up with in your calculator. And since nanometers is 10 to the negative 9th meters, that's 437 nanometers. Okay, and there is one other part to the test, which is going to be a periodic table puzzle, sort of like we did a couple days ago in class. That will be posted as a practice version of that will be posted as a separate video. So that's it for the problems, and then the periodic table puzzle will be posted as part 2 of this review.